Okay. Yeah, you're going to get the test back tomorrow. All right. Any others? All right. The next example we're going to look at is adding 1 drop of 6 molar HCl to 100 milliliters of buffer. This is going to be 100 mil pH 7.00 buffer. Now, the pH 7.00 buffer, all we have to do is get the right ratio, right? But it's not just the ratio. We also have to look at the capacity. The capacity of the buffer is, what is the concentration we're going to have for those acid and base components. The more concentrated it is, the higher the capacity it has. And capacity is the ability to neutralize added acids or added bases, like this. And so when we're thinking, but the higher the capacity of the buffer, the more expensive it is. So you might not need all that capacity. And so what were the concentrations for a pH 7 buffer? What's the base to acid? What was it, 0.57 molar or something like that? We use the dihydrogen phosphate and monohydrogen phosphate.
0.512.
0.5122 molar base. Is that right? Okay. Monohydrogen phosphate, we're calling this the base. But isn't monohydrogen phosphate amphoteric? It's amphoteric, so we shouldn't just call it a base because it also has a acid reaction as well. And so how are we justified in calling this the base when it really is an acid and a base? It's not because of the Kb. It doesn't really matter what the Ka and the Kb are for this particular case.
Is it because we're adding 1 drop of acid?
No, it's not because we're adding 1 drop of acid.
This hydrochloric acid is not acid.
Well, we could have added base here. We could have added 1 drop of 6 molar sodium hydroxide, and we'd still call this the base. Why?
The acid in the solution.
Yeah, there's an acid in the solution that's more acidic than this. What is the acid in solution that's more acidic than this? Dihydrogen phosphate. And so the reason we call this a base is because we have a stronger acid present. And what's going to react first? The weaker acid or the stronger acid?
Stronger.
The stronger acid is going to react first because it's much easier to pluck a proton off a strong acid than a weak acid, right?
How do we have the hydrogen?
Because this is a buffer. In the buffer solution, we're going to have a base and an acid component. This is the problem we were doing yesterday. And so since we have an acid, a stronger acid present, this one will not act as an acid, even though it can act as an acid. This is amphoteric also, right? Dihydrogen phosphate is amphoteric, but here we define it as an acid. The reason we define it as an acid is because there's a stronger base present, and therefore we don't have to worry about the base properties of this, right? Having a stronger base present. And so yes, these are amphoteric, but the mixture defines their role. The mixture always defines the role because hydroxide, did you know hydroxide is amphoteric? If you look at the acids chart up there on the board, on the wall, you'll see hydroxide occurs on both sides of the chart. But normally we think of hydroxide as a strong base. How could it react as an acid? The only way it can react as an acid is if you have an extremely powerful base. more powerful base than oxide present. Does that make sense? And so the role that they play depends on what you react it with. Like, and that goes for everything. Does water burn? Is water, things that burn are decent. Well, the oxidizer is what's burning it. So like wood burns, right? Paper burns, gasoline burns. Those types of things burn because they have electrons, right? And the oxidizer comes in and takes those electrons in a redox reaction. So we need an oxidizer. The oxidizer itself, we don't say it burns, but we need an oxidizer for combustion to take place. And so when you think about water, is water a good fuel? I mean, would you use it to build a fire? No, because oxygen is not a powerful enough oxidizer to oxidize water. It's just not going to happen. Water will not burn, right? But what if you use a more powerful oxidizer? Like for example, does stainless steel normally burn? Stainless steel doesn't normally burn, but you could get it to burn, like actually make a fire out of using stainless steel and not oxygen, stainless steel and no, CO2 is actually much worse of an oxidizer than oxygen. It's pretty fluorine, right? Fluorine is a more powerful oxidizer than oxygen and actually can catch stainless steel on fire. And so that stainless steel acts as the fuel. Stainless steel, I picked stainless steel because stainless steel is an alloy that's formulated to resist corrosion, resist oxidation. And so it doesn't rust like normal steel. But do you know you could catch water on fire? Water will burn if you have a powerful enough oxidizer. And so there are some exotic oxidizers like one O2F2. O2F2 is a powerful enough oxidizer to catch stainless steel fire. O2F2, if you release methane into this room and there's fluorine present, you know what's going to happen? Instant fire, right? It'll explode. But if you release here into O2, are you going to get a fire instantly? No, it requires a higher temperature. So you got to increase the temperature. This is something I just read. With O2F2, you know what the temperature of the ignition or the explosive temperature for methane and O2F2 is? That's like minus 300 degrees Fahrenheit. It'll explode, and so you have to. So the instant it comes into contact with it, it's going to explode. So yeah, it's all relative. It depends on what you're reacting with, but we don't want to worry about all those things. So we look at typical reactions over a typical range. Like from fluorine to lithium, and the more exotic oxidizers and reducers, we aren't necessarily going to worry too much about. And so water is very stable in our normal realm of things, right? Water we don't think of as burning, right? And so this is it. But the thing is, you don't want to get into this fixed mindset. Just because we have a range, a normal range, right, doesn't mean it can't go beyond that range, right? It's like pH. The normal range of pH is 0 to 14, but can it go beyond that range? Yeah. But some people think it can't. Just like they think, well, water can never burn, but because, there's potential. So there's some things that won't, because they don't have any electrons to give up. And there's nothing powerful enough to oxidize it. And so, yeah, even though these are amphoteric, their behavior is dictated by what you're mixing it with, or what we have in here. Okay. And since we have both of these here present, then that's it. How would I increase the capacity of this buffer? Without changing the pH, how would I increase the capacity? Yeah, I could add more, make these more concentrated. So rather than 0.5, I go to 5 molar or something like that, or 1 molar here. You know, I just make it more concentrated, keep the same ratio. That'll do it. Or I can make it lower capacity. You know, and so this is always tricky because you know, it's like if you buy a liter of helium gas. You know, a liter of helium gas, does that tell you much? No, because you don't know, you know, what the pressure is. If it's a liter of helium gas at 1 atmosphere, that's not much helium, right? Versus if a liter of gas at 1,000 atmospheres, that's a lot of gas. And so just because you have a pH 7 buffer, you don't know what its capacity is. You know, somebody could have just watered this down and watered it down, right, until it's got very little capacity. There's really nothing there. So we don't want it too watered down. We need it to effectively neutralize something like this. And so let's see what happens when we add a drop of this. And so what we do in chapter 17 is we do step I. What was step I again? Well, that was earlier, chapter 16. Sorry, maybe I should use a different. Step A. We do step A.
Solution dilution.
Solution dilution. We have to do solution dilution because it depends. You know, 1 drop is not really going to dilute these much, right? But 100 milliliters will significantly dilute this. And sometimes we add a lot more, like 20 milliliters. If we add 20 milliliters of this, you know, this is a significant solution dilution for everything. And so the first thing we always do is we calculate the total final volume. The total final volume will be what here? 100. 0.05, assuming a drop is about 0.05 milliliters, right? And so we go 100.05 milliliters. And then we calculate the new concentrations of everything. We don't do any reactions yet. Step A, we never do reactions. We just do strict solution dilution, see what the new concentrations of everything will be. What's the dilution factor for HCl? Dilution factor for HCl is the original over the final times the original. And so we already calculated this. What was the concentration here? 0.00299. All right. Technically, we're only allowed 1 sig fig, but we never want to round to 1 sig fig because it leads to huge round-off errors at the end. You know, it's like the proportions. Like a 1 drop error. A 1 drop error, if you have a billion drops, is nothing, right? But a 1 drop error, if you're only counting like 5 drops, is huge, you know? 5 drops plus or minus 1 versus 1 billion drops plus or minus 1 is a big difference. So when you go down to 1 sig fig, you're introducing these enormous round-off errors, which you never want to do. And then we're going to go to HPO4 2 minus. At the end, we can round it off, of course. The new concentration of the HPO4 2 minus is, you know, we're taking 100, diluting it to 100.05 times the original, which is 0.5122 molar. And so this is barely diluted, but we might as well calculate it so that we can minimize the error in our calculations. .5119. Okay. Molar. And then we have H2PO4 minus. It's 100 to 100.05 dilution times original molarity, 1.00 molar, which gives us 0.9995 molar. So these are the initial concentrations, after solution dilution. But these are the initial concentrations for the reaction. And what is the reaction? Well, that brings us to step 1. And so in chapter 17, we all do this. This is the same method we used in chapter 16, except we only had one other species present, that was water. Right? And so water was either the acid or the base or acid that we were adding to water reacted with. But that's not always the case here. And so step 1, react the strongest acid with the strongest base. Strongest acid has the most loosely held proton, and the strongest base is the one that's going to attack that proton. And so what is the strongest? Well, we have some choices. We have HCl, HPO4 2 minus, H2PO4 minus, and water. And water. And so this is pretty much our starting inventory. And so which one is the strongest acid? Which one is the strongest base? Well, we usually do HCl and water, right? That's Ka. But is water really the strongest base now? No. What is the strongest base? HPO4 2 minus. And so the reaction we have here is HCl plus HPO4 2 minus is going to give us H2PO4 minus and Cl minus. Now, we have to figure out what is the K for this reaction. No, that's only for Ka and Kb. This is neither Ka nor Kb. This is K of reaction. Ka is acid plus water. Kb is base plus water only. This is acid plus some other base, not water. You should know this. It should be automatic. You should have seen this several times by now, because I talked about this like last week or week before last. Right? It should be automatic. You should see it right away. No. Close. Very, very large. This should have been automatic. I'm surprised it took that long. Very, very large, right? Why very, very large?
Because it's strong acid.
Yeah, it's a strong acid weak base compound. Strong acid weak base compound. I know that's memorization, but the way to memorize things is, for me, is repetition. I have a hard time memorizing stuff unless I see it repeatedly. Well, if it's very, very large, then let's go ahead and put the concentrations in. The concentration of HCl is 0.0299. The concentration of HPO4 2 minus is 0.5119. The concentration of H2PO4 minus is 0.9995. And the concentration of Cl minus is 0. Yeah, it's going to be minus, minus, plus, plus, but if it's very, very large, it goes to completion. So all we do is look for the limiting reagent, which would be HCl. So the limiting reagent is going to be completely consumed, and so we're going to lose 0.00299 here. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. So that's going to be 1, 18 would be 9, 10, 8, 0, 5. I get 0.50889. Is that right? And over here, we're going to get plus 0.00299. It's all 1-to-1 mole ratio. So this is going to give me 9, 4, 10, 12. Is that right? 1.00249 molar. And then 0.0299 molar chloride. All right, when K is very, very large, you know, it's just a one-way reaction. This is just plain straight stoichiometry, Chem 1A style. Are we done? All right, done. Okay. What we do next is look at what type of solution remains. And then, you know, we could repeat, for example, we might repeat, you know, the strongest acid with the strongest base reaction. So here, what is the strongest acid present? Dihydrogen phosphate. What's the strongest base present? Monohydrogen phosphate. So what's the reaction? When you take dihydrogen phosphate and monohydrogen phosphate and react them, what happens? Well, we get the same thing, right? If we take H2PO4 minus plus HPO4 2 minus and transfer a proton, then we're just going to get HPO4 2 minus and H2PO4 minus, right? So nothing changed. And so does that mean we're done? No, because do you recognize this? This is a weak, this is a buffer, right? If this is an HH buffer, HH buffer will be Henderson-Hasselbalch. Henderson-Hasselbalch buffer is a special buffer in which the acid and the base are conjugates of each other. And this is the case. This is a Henderson-Hasselbalch buffer. Then we could use the HH equation. Right? We don't have to set up another ice table. We just go ahead and use the HH equation because these concentrations really aren't going to change. And so we can go for the pH. The pH of this is going to equal the pKa plus the log of the base to acid ratio. And don't forget, this is always for conjugate. Sometimes people just try to apply the Henderson-Hasselbalch to everything. And so, for example, they see, oh, HCl is the acid. They'll put HCl down here, and the base, HPO4 2 minus, they'll put it here. That doesn't work. Let's see. And so what was the pKa of H2PO4 minus? It was like 7.20 plus the log. The base is going to be 0.50891 over the acid of 1.00249. And that comes out to it should go 6 point something, I think.
Yeah. 6.905.
6.905. It dropped that much? I need to. Can you double check that calculation, please?
How'd you get to 7.20?
6.905 is what everybody got? 6.905. How did I get the 7.20? I got it from before, you know, because I know the acid is H2PO4 minus. I skipped some stuff. All right, well, basically this is what happened. We make a comparison. We add a drop of 6 molar HCl to 100 milliliters of water, unbuffered. pH dropped to 2.5, let's say. We add a drop of 6 molar HCl to this buffer solution. What happens? pH drops to 6.9. And so do you see how the buffer prevented the pH from changing much? The buffer minimized pH change by neutralizing the acid. In this case, HCl. But it came at a sacrifice. And the sacrifice that it came at is like this, pKa plus the log. Now, if we add acid, you know, we have the base here. And so that's the initial base. It's going to lose X, right, from the acid. And the acid here, what's it? Is going to increase plus X. And so the higher the concentration initial, the greater the buffer capacity, because if you lose a little bit or gain a little bit, it's not going to have much of an impact. The lower the capacity of this, right, the bigger the impact is because the ratio will change more significantly here. And so if I had 1 million molar base and 1 million molar acid, then losing this much isn't going to have any kind of impact at all. Is it possible to have 1 million molar? No, that's impossible. But versus if I had 1 millionth. If I had 1 millionth of a molar, 1 millionth of a molar, then losing a drop or gaining a drop is going to have a huge impact on that, and it's going to change the ratio significantly, which is going to result in a much more dramatic pH change. The thing I have to watch out for is exceeding the capacity of the buffer. What I mean by exceeding the capacity of the buffer is adding so much acid that I end up reacting all my base. And then not only that, if I react all my base and I have even more acid, then I'll have excess HCl left over. And so let's see an example of that. You know, I only added 1 drop. 3, 500. So let's take a look at an example of exceeding the capacity of this buffer. With this time I'm going to add base. So how much should I dump in here? I'm going to put in some 6 molar sodium hydroxide. How much do you think it would overwhelm this buffer? We go with 20 milliliters, 50 milliliters, what should I do? 100 milliliters? 25 milliliters? Let's see, let's try to keep this solution dilution simple. 10 milliliters? Will 10 milliliters do it? Let's see if 10 milliliters does it. So I'm going to go with 10.00 milliliters of 6 molar. We're going to add this to 100 milliliters of the pH 7 buffer. And this pH 7 buffer, we'll just keep it the same, 0.517 molar base and 1.00 molar acid. All right, why don't you start this one here?